Hello and good afternoon. My name is Charlie Bender, and we are welcoming you to the first hydraulics webinar, which has been organized by AIST's Lubrication and Hydraulics Technology Committee. I am a staff engineer here at AIST, and I'd like to go over a couple of elements of the webinar that should be familiar for people who attend AIST conferences. The first one is the Antitrust compliance statement. We have several statements that we all adhere to. We do not choose to discuss others, your own competitors' pricing or pricing procedures, or profit margins or anticipated wage rates. Don't make statements about prices or those of your competitors or individual plans for markets with your customers or others' customers. These are in enforcement of the United States antitrust laws. The second statement is an AIST anti-harassment statement. The Association of Iron and Steel Technology is dedicated to providing a harassment-free event for everyone, regardless of age, race, religion, disability, gender, gender identity, or sexual orientation. And AIST does not tolerate harassment in any form. Harassing behaviors include offensive verbal comments related to age or race, religion, disability, gender, gender identity, or sexual orientation, the use or display of sexual images, activities, or commentary in public spaces, deliberate intimidation, stalking, or following, harassing photography or recording, and sustained disruption of events. These are inappropriate. With these statements, we'd like to help you become familiar with the Zoom product. Each attendee has been muted. Their audio is held. You'll be able to hear our host, our presenter, and if you would have questions, take a look at the Zoom product. At the bottom, there's a question and answer feature. Some of you that may be at the top of the screen, but please feel free to type questions in. They will be submitted to Steve, our moderator, who will package them for Brad to be able to review and answer at the end of the session. This session is being recorded, and you will have a hyperlink at the, give us a couple of days and it will be available on the AIST website. And for those attendees that are having technical difficulties, please feel free to email directly to training@aist.org, and we'll be able to help you improve your Zoom session. There is one more important reminder. Photos or recording of these presentations are strictly prohibited. At the end, you'll be given a link to our presenter, Brad, and in a couple of days, the recorded webinar up on the AIST website. With that, I'd like to take a moment and introduce our moderator, Mr. Steve Heaviside. Steve is Director of Corporate Reliability system-wide for Evraz Steel North America. And he has been in the steel industry for 22 years, being a part of several startups across North America in increasing roles with maintenance and reliability. In his current role, he promotes understanding and learning from events and occurrences that are experienced in all aspects of steel mill operation to improve cost effectiveness, product quality, machine uptime, and risk management. Steve is deeply passionate about creating the next generation of craftsmen and adapting the latest technology to bridge the skills gap. Steve sits as chairman of 3 apprenticeship committees for the Oregon Manufacturing Innovation Center and is currently our papers chairman for the Maintenance and Reliability Technical Committee. With that, I'd like to turn over the presentation for Steve for Mr. Brad Jensen, our presenter.
Thank you, Charlie, and welcome everybody to today's presentation. I know Brad and AIST have done a lot of work to make this happen. So coming up, you'll be hearing from Brad Jensen. He's our technology consultant with Alloy Technology Solutions. Brad is the past founder and patent holder of IntelliSchematic. He has more than 25 years of experience in industrial training and troubleshooting and hydraulic motion controls. He is a certified fluid power specialist by the International Fluid Power Society and served for a number of years on the IFPS Board of Directors. His industrial troubleshooting experience comes primarily from the steel manufacturing industry, where he works today as a technology consultant for Alloy Technology Solutions. Brad has a Bachelor of Technology degree in automotive. With that, Brad, I'm going to kick it over to you.
Well, thanks, Steve. It's good to be with all of you for a little bit this morning or this afternoon, depending on what part of the country that you're from. Although we're going to be talking a little bit about hydraulic troubleshooting and technology, new technology driving it, I want to emphasize that the technology that we're talking about is applicable to all facets of the industry in manufacturing, process plants, etc. I was in Nigeria last year working with this same technology with Shell. So it fits the oil and gas, it fits virtually every industry. I'm just going to give you a piece of the technology today in an application that's related to hydraulic. But before I get to that, let me first advance my slide here. Okay. Let's talk for just a second about the Internet of Things, or Industry 4.0. You've heard a lot about that. It continues to grow massively, exponentially. And what it basically is focusing on in terms of the technology that we're talking about is connecting huge amounts of data to smart devices. And that continues to make troubleshooting very, very easy. And it fits the incoming generation of technicians that we have with us joining us today. Much of the data that it's amassing, and you got to understand the data itself is being driven by connectivity. And this data is public domain, or it's produced by the OEM, or it's produced by subject matter experts that drives this interconnectivity within the industry. And it makes maintenance not only more efficient, but extremely much more safe. The type of technology that links huge amounts of applicable machine and system data to existing schematics and P&IDs, sophisticated process flow diagrams, and etc. It is intended to put this information at your fingertips. And that's what I want to emphasize, particularly today in some of these applications that I want to share with you. One such patent application that we're going to show you that fits into this Industry 4.0 or the Internet of Things is what we call the iMachine. The iMachine application, it's a software application that basically puts content into context, as I would like to put it. When a new machine is commissioned or a system goes online, you have massive amounts of data associated with it. And that data can be broken down into different segments for different uses. For example, a huge amount of data from a downcoiler, for example, in the steel industry, a small amount of that would apply to someone that's troubleshooting it on an unscheduled outage. But obviously he needs it. He needs that data at his fingertips, and he needs it immediately. So if we can take and index all that data and associate it with the machine's events, we are way down the road in terms of the amount of time it takes to troubleshoot and troubleshoot safely. And I just want to emphasize again that this technology applies to your water management in your plants, lube systems, single line. We've done a number of single line systems on incoming power, HVAC, overhead cranes, whatever. But for today's discussion, we're going to focus on one of my favorite areas, which is hydraulics. So when we began to troubleshoot hydraulics in particular, there are existing gaps that have been there for a number of years and continue to be there that we have to close to do it effectively and to do it safely. I'll get to more of those gaps as we get into this actual application that I'm going to share with you. But some of the things that I bullet pointed here for you is the accuracy of the schematics and the component application, understanding them, the component location, and bridging over into the controls, which is any application, whether it be electrical or hydraulic or pneumatic or what have you. So to make this application real, we have to take a machine. The machine I'm going to apply this to is a hydrotester. It happens to be at Portland Everaz pipe mill. It is in its own right, a fairly complicated piece of equipment because you're dealing with three sources of power transmission and controls. Two of them are hydraulic and one is water control. So I'm going to toggle over here to the there we go. Okay. So when you look at a machine in terms of understanding it and applying a technology such as we're applying here, you have to understand that a machine has different, what I call sequence of events or operations that it performs in sequence to produce what its intended purpose is. And if I break those down, it makes the approach of troubleshooting very, very easy. So we always index, this application indexes different areas of the machine that you might need to go to immediately. It's in the left-hand navigation here, we have an overview, which is incredibly important. If you're new, a new hire, or you're new to that part of the mill or whatever, you might not know what the machine is actually doing. Overviews are also very, very good for people that are operators to understand basically what is going on. And that can be generally as deep as you want it to be or as basic or summary as you'd like it to be. And then we've got, at least in this piece of equipment, we've got the hydraulic power unit, the main hydraulic power unit. We have the water system. We have pipe handling. We have what we call a movable frame, which is positioning the machine so that it can fit a certain length of pipe and control the pressurization of the water coming in. And then under the last main category, I have the bill of materials. So if I were looking at troubleshooting this on an outage, the first thing that's going to happen is that the operator or somebody is going to inform the troubleshooter that something is not happening or something is happening, and where is that occurring? Let me go, for an example, to pipe handling. Let's say that there's a problem on pipe handling, and within the category of pipe handling, we've got pipe entry, we've got pre-test, and we've got exit. If the problem is in entry, we simply click on entry. Now we have photos of that part of the pipe mill and what is, or excuse me, the hydrotester and what it's doing on handling the pipe that's coming in. And you notice in the right-hand column over here, we now have images that identify the manifold and the valve stacks for each of the events that are located down here at the bottom of the screen. So what we have done is we have taken the schematic, excuse me, we've taken the machine and broke it down into categories of operation and further broken it down into different circuits that we can move to very quickly. And these circuits in this application are related to pipe handling. So if we go over to all of these events, each one is supported by a schematic. Let's just say that we're looking at the kicker cylinder number 4. And you'll see right here, I think it's impossible to troubleshoot hydraulics without a schematic, although it happens every day. And if you're familiar with the circuit, that obviously helps, and sometimes you can get by without it. But without having a schematic to read and understand where the flow is, you're just kind of winging it. So the first thing that we want to indicate here is a schematic that is accurate and actually exists. In most plants, when there is a problem, a serious problem, and the troubleshooter is trying to get it back up, even finding the schematic is sometimes an issue. So the first thing that we ensure is that we have accurate schematics. Reading the schematic is another process. So you'll notice here that this is color coded to indicate, and I'm going to zoom in here, the condition of the fluid as that circuit is functioning. And we have over here a legend that tells us that the red is system pressure, blue is exhaust flow, we've got case drain, yellow is metered flow, we've got orange, which is reduced pressure. These are all ISO industry standards. So if you were looking at, I know some OEMs such as Caterpillar are very good at showing you the different ISO color layers in their schematics so that you know what the condition of the fluid in the circuit is at any given time. So from this, we can look at the circuit, recognize with the color what's happening. We can see that the component, in this case, has shifted, but we don't maybe know what the component is. If you roll over the bubble, we have associated that bubble with the device, which is a directional control valve. And up in the upper left corner of your screen, you should be able to see where we have actually arrowed that directional control valve on the system. So it's one thing to pull the schematic out and begin to follow it, but it's kind of another thing to identify and understand what the components are or what the symbols indicate, and again, where they're located. Now we're looking at a pretty simple stack valve here, but if I had a block with logic valves bolted all over it, it would be a very, very difficult circuit to try to identify and understand without the schematic. And even with the schematic, identifying where the component is on the manifold. So in addition to identifying where it's at, what it is, you have the manufacturer, you have the part number, and we'll get to this in a bit, but you have the electrical address, the controls, what's firing it. And then down here, you have a description of what that device is doing in that particular circuit. In other words, if you look at pressure valves, we basically have 5 different types of pressure valves. But within those 5 designated types of pressure valves, you can have various applications within each valve. You can have counterbalance valves being used in 1 or 2 different applications. Relief valves, what is common to some as just a relief valve, might be used in a different application. But it tells you exactly in this circuit what that directional control valve is doing. It tells you that it's a float center. That gives you good information and tells you exactly what's going on. This 3-position 4-way float center directional control valve controls the position of its downstream actuator. In the P to A flow position, it extends the cylinder while exhausting the rod side cylinder flow back to the reservoir. In the P to B porting position, the cylinder is retracted, exhausting flow from the piston side to the reservoir. So it goes into detail on exactly the application and how it's functioning. If you are rather new to hydraulics and you want to know how it works, again, this is another piece of that resource with the industry that we now live in that we pull in and link to. And this is an animation that shows exactly, in this case, how a directional control valve functions.
A direct-acting directional control valve is either manual or solenoid actuated. Direct acting indicates that some method of force is applied directly to the spool, causing the spool to shift. In this illustration, energizing the solenoid or coil creates an electromagnetic force, which pulls the armature into the magnetic field. As this occurs, the connected push pin moves the spool in the same direction while compressing the return spring. As the spool valve shifts, port P opens to port A, and port B opens to port T or tank, allowing the cylinder to extend. When the coil is de-energized, the return spring moves the spool back to its center position. View the entire animation uninterrupted.
So you can see that would give somebody that's not familiar with this particular hydraulic component a good understanding. And that is attached to all of the components throughout the iMachine application. Also, I think this is one of the most important pieces of data that's pulled in from the cloud and connected in. This is the component data sheet. This is priceless. This is, in this particular case, it's a Rexroth data sheet on that, that device, that control valve, directional control valve. And you can see that it covers everything from reordering the right spec, the nomenclature, to actual training on how the valve functions as well. And so these are also attached to all of the components that are part of the circuit. So going back to where we're at in the circuit here, this shows that in this case, the valve has shifted and we're in the extend mode. Also down here, if I can get rid of that thing on the bottom. and go to retract or to extend. So you see as we shift between retract and extend, the circuit shifts along with the color coding on it. Now, let's go back out of this and look at some other areas. Here's the hydraulic power unit. You can see from this, I'm going to go down. The HPU, the hydraulic power unit, it in and of itself has different events that it can be in. It can be either loaded or unloaded. And as I click on those circuits, this one is unloaded. And this, by the way, this HPU runs the framework, and it also is powering the incoming pipe controls. But if I go to the unloaded, you can see that we are along the same color coding here of what's happening. But we have a little bit more complicated application, because in this particular HPU, we've got one of those manifolds that have logic valves bolted all the way around it. And again, I can't emphasize how important it is to be able to have a schematic that's accurate, that you can read, so that you're not pulling one of those off, heaven forbid, under pressure, not knowing which one you're on. The same thing, we have an animation that...
Slip-in cartridge valves, also known as logic valves, use an insert consisting of a poppet, spring, seals, and a sleeve. The insert slips into a cavity machined into a manifold block.
We won't go on that. And we also have the data sheet that goes with it. Now, let's go back to for the sake of time, let's say that we have a problem back on that, that kicker cylinder in pipe handling. If I've got an outage, the operator says, well, the number 4 kicker cylinder on pipe entry won't extend. Well, immediately I know where I have to go. I go into pipe handling. I go into entry, because that's where the kicker cylinder is. I go here to the number 4, where we just were. I click on extend, and I can see in this position what's happening here. This valve is shifted to this position, P to A. I'm going through a set of PO check valves because there's a float spool here, and when I'm in neutral, this has to hold position, but I'm not getting any extension. Possibly it might be in my flow control valve here. And again, it's the same thing. I roll over it. It shows where it is in the system, how it functions, and etc. Stranger things have happened. Maybe somebody on the swing shift tried to fix it, and they screwed the flow control valve all the way in. I have here another piece of this data that exists out there. This shows the direction of fluid flow. This shows how you would pull that flow control valve out, and you can see by the symbology here that it's kind of critical which way it goes in. I can change from meter in to meter out just by rotating the valve. Well, for someone new that's never done that, it's nice to be able to put that reference there.
First, by looking at the schematic symbol on the valve. Loosen the 4 hollow hex head cap screws and remove the DO3 directional control valve.
There's an important part here. I'll let this run for a minute and you'll see what I mean.
The dowel pins are used to orient the valve P port on the manifold or subplate, so it cannot be installed backwards. This will need to be moved to the correct valve interface side. To change the flow pattern, flip the flow control as shown. Remove and replace the dowel pin on the other side. Replace the seal plate. Check to see the seals are undamaged. Reassemble the valve stack. Torque the hollow hex head bolts to 80-inch.
Now you notice he replaced the seal plate. That means that that valve can, as you saw here, it could be rotated either way. If it was rotated the wrong way, that cylinder is, or the functionality of that kicker cylinder is going to be completely backwards with the controls.
Pounds.
So let me end this. Go back, and again, we've got component data. And if maybe that's not the problem, maybe that doesn't solve it. We go back to the coil, and we find out that the coil is good. It tests out fine. But wouldn't it be nice to very quickly jump over to controls and see if everything is fine there, or where the IO addressing is. I know that if the coil is fine, if I go back to the cabinet and all the permissives have been met, then I may have, it may just be a wire connection, or in this case, a fuse. But how nice is it to roll over and see, okay, that's the coil that gives me an extension. This is the fuse. Steve will probably verify that this is common in on this machine in their controls.
Yes.
Or Mr. Brown will tell you that. And right here is where the signal comes from, in this cabinet. So can you begin to see how we've taken troubleshooting that is perhaps this time consuming and have brought it down to what I call the last mile, of where you're going to have to think on your own, but at least you are very quickly right at where you need to be. And I could take you through this and show you example after example of how quickly every aspect of this machine can be troubleshooted safely and very quickly. Even through the water system, you can see on the piping system here, you've got water over here, high pressure, being routed to hydraulics that's controlling the positioning of the frame, a very complicated arrangement of a pre-fill application, and then another small hydraulic power unit that's controlling these different valves that are opening, closing, and directing the water into the test and back. I also want to mention how valuable the bill of material is. And again, once this information is pulled in to the iMachine software, it's manipulated and linked to wherever you want it, wherever it needs to be, I should say. I won't mention who the manufacturer is. It's a large airplane builder, all of their systems use, not all of them on some of their new plants, but they use this iMachine. And one of the people in stores told me that just being able to identify when he gets a request for a part that needs to be changed out on the floor, to identify that it's actually the right part, more than covers the pain of getting this integrated into their system. Because once the part leaves stores, if it's not the right part, sometimes it doesn't make it back to stores, if you know what I mean. So anyway, you can do a search here. If I wanted to pull up flow control, okay, this gives me all the flow control valves on the hydrotester, the bubble numbers here, and obviously I can click to it and it takes me right out to where it is. That's the flow control valve on that manifold, etc. So I hope you can begin to understand that the power of these applications that are cloud-based, that forever improve the efficiency of your troubleshooting and forever keep everything clean in terms of updated documentation. It's important that you understand, this is on a slide, but I won't jump back to the slides. Troubleshooting is a process. It's not an event. If troubleshooting is an event only at your location, you want to change that. Take the tools that make troubleshooting a process and get people familiar with it and stick to it. Also, an important, you might say, well, Brad, what about changes? What if, I mean, changes happen all the time on equipment, particularly hydraulic valving and whatever is changed out. What do you do about that? Well, there's a very easy solution. You click on the report change button down here, and it pulls in all the information that should go with this. You submit it, it goes back, and all the support that you need to update that is taken care of. And we have at different locations, some people are completely involved in doing that themselves. Others have people that are using or that are supporting the iMachines, supply that support for them, and etc. But immediate updates are critical, and they're easy to do. And that's a very important feature. I guess at this point, looking at the time, do we have any questions? Steve?
Yeah, Brad. Brad, can you hear me? Hello, Brad, can you hear me?
Yes.
All right, so we do have, we've had 3 questions, one of which I went ahead and answered in the panel, but I'll go ahead and state it out loud, and then we'll go to a couple more. Kevin Morrow had asked, what are the leading coding platforms being used for IoT in the industrial manufacturing space? My answer to him was, there's a lot of them, about 15 different languages currently being deployed, but the top 5 or 6 are Java, C, JavaScript, Python, C++, PHP, and so on down the line. Does Wes or you have any input on that?
All I can tell you is this, we build everything and everything is in HTML5. It's very easy to manipulate, embed, connect to CCM cloud-based. This is not complicated software at all. The patent actually is a process patent. It's not code.
Yeah, that's for your platform. But even when we're talking about IoT sensors and the ability to read what's going on within a system, a lot of those sensors are using these other languages as well.
Yeah, I'm really not that familiar with that aspect, Steve.
Not a problem. Koskin asked, as he understands it, this is just a tool for maintenance stuff to check schematics and location of components and etc. There's nothing we can see any diagnostic info or signal, correct? If not, would it be great to embed these diagrams into operator stations, HMI, especially in these critical processes such as high ROP, roll gap, roll coolant, and so on? Figure I'd let you take a stab first, and then I'll talk about some of the things that I know we're pushing for in relation with you and others.
Yeah, that is true. It's not real time. And we have embedded these in HDMI applications. And they're very, very effective that way. Some companies are not yet there with tablets on the floor. Connectivity is growing exponentially. But yes, it's very effective at the machine itself. We are moving quickly into barcoding to where you can actually out on the machine or in the power unit pump room, you can barcode or scan over the barcode and bring up all the data, including the actual circuit and all the data that I just illustrated here.
Yeah. So if you don't mind, I'll wade into it just for a minute. And this will help with Koskin and Joseph Monterola's questions. They're both kind of tied together. As we progress down this path of technology, some of the things that I'm working on with people like Brad and others, such as I'm not sure if anybody knows Eric Almquist of Star Tool, as well as others. We're starting to develop the ability to utilize wearable computers, tying IoT sensors into those wearable computers, basically through the PLC, have a front end display similar to what Brad is showing you, and have the machine tell you where it's hurting. Instead of, as a reliability guy, our biggest waste that we have is we're going out to troubleshoot. Most of the craftsmen don't understand the system. They're digging through drawings, they're looking at the wrong thing, and they're assuming instead of having the equipment tell them where it's hurting overall. Utilizing things like the HoloLens, RealWear, or even just a simple tablet computer or your phone, you can have real-time output from the equipment giving you pressures, temperatures, fluid cleanliness readings, vibration analysis, all these types of things that are tied directly into the front end, like what Brad's company is presenting, and tell the craftsman or the troubleshooter on the floor exactly where to go and look. And oftentimes then Brad's company and others like him can take that information and say, if you see this, then go do that. And really that's the beauty of something like this. You want to add anything to that, Brad?
No, I yes, that you've hit it all right on the head. I like to emphasize that this is simplicity, and it's extremely homogeneous to the millennial generation coming in. And I don't talk about it much in terms of, I mean, this is primarily a troubleshooting tool, but I know Nucor and several other places use this to do their machine-specific training. And Boeing has done that for years. A hydraulic person or whoever is a controls person, whoever is over a certain area, he can take the iMachine on a particular machine that he's doing some training on, and within 2 hours he's up to speed. He doesn't have to develop anything at all. It's all ready for him to pull a class together and walk through the system, and it's quite powerful that way.
Yeah, absolutely. And we have utilized it in much the same way. When we started up our recent startup of our spiral facility, these types of tools were very important to get new tradesmen as well as operators to understand exactly what's going on with a piece of equipment. So how do you measure? This question comes from I just lost it, sorry. Myrnell, he said, have you tried to determine annual savings for a particular system or mill that is realized by utilizing this type of troubleshooting technology or machine learning technology?
Yeah, absolutely.
You want to take a step first?
Absolutely. 4 years ago, I integrated this into the Hadid mill in Saudi Arabia. And that, you that are familiar with that is, I think it's the third largest steel producer on one footprint in the world, other than one in India. It took 2 years, but the maintenance superintendent was on course for determining the metrics or the difference. As you know, not to get into the Saudi culture, but as you know, they're trying to train their own people now instead of hiring it out. And the learning curve was incredible. They were able to actually, and one metric was they had to have, on the hydraulic side, they had to have fluid power specialists, at least one on every shift in every area of the mill on the night shift. And within 6 months of adopting this as a process in troubleshooting, they were able to remove those key subject matter experts and put them back into their day swings. That's one example. Another example is I do have information from a mill and a Nucor mill that documented the savings on this, and it's fairly objective. Sometimes something training, as you know, can be subjective. You have to have metrics that are real. And another place I have documentation from a gold mine in Nevada, Barrick, that uses this, and they punch in when a haul truck comes in. They punch in when it came in and what the problem is, and how long. When it's fixed, they punch it out. So they took all the data over 1 year and compared it to the years before, and it was so astronomical the upper level wouldn't publish it. They said that's impossible. But if you're measuring unscheduled outage, non-recoverable, it's going to be huge, the savings.
And if you don't mind, I'll weigh in as well from a personal, from my mill's perspective. I'm not sure how many people know, but we recently had a ransomware attack take down all of our servers and intra and intranet at our mills. And the spiral mill was in the middle of production. We couldn't access our CMMS. We couldn't access a lot of information that we had stored on the cloud. And we had a hydraulic system failure. And we were able to go straight to this product right here within a matter of seconds, find out exactly what it is we're looking for, call our vendors, and get the component coming. It had the potential of keeping us down for some time, but it's hard to capture what that type of savings is. But I can tell you, as the superintendent of maintenance at the time, it was huge. It was a huge savings for us. So can't really quantize it for you, but this is being done repeatedly. Brad got a couple more questions from Carlos and Andy. It's a similar question phrased a couple different ways. So I'll read Carlos's first. What is the average time required to load all of the schematics for a system of about and up to 1,000 signals for reference? Do plants usually have one person assigned to keeping this current as system and log repairs happen? I'm asking because some of these systems become an additional time load to keep current. I'm going to go ahead and ask the second question alongside of it because it kind of follows in line with this. When equipment is replaced for whatever reason, how easy is it to update the relevant schematics, pictures, videos, documents? Is there a system smart enough to know when you replace update equipment that the old documentation tied to the equipment is no longer relevant? I know that we have a lot of history with that, but I'll let you go with it.
Well, first of all, updating or time in taking the schematics, it depends on what is currently available. And we've gone from machines that have no schematics, or at least extremely outdated, to machines that are just commissioned and have schematics that are nicely, they're done well, they're easy to convert over. We do not, although we can output them in a Pro-E or any other DWG format, we actually convert them into a program called Illustrator, Adobe, which most people are familiar with, and we layer it so that when something on the schematic needs to be changed, it's very easy to update. In fact, there's a mild, I'll call it a mild, yearly access that keeps everything updated for you, that covers all that. And again, it's very easy. For one method of capturing video or images is simply to use an application that we have patent pending on, which takes and once you shoot from a smartphone, your smartphone, and a phone, an iPad, or whatever, once you shoot it, it brings an arrow up that with your finger, you place the arrow. It asks you if you like the photo. Do you like the perspective? Yes, yes. Do you want to upload? Yes. And it goes up and attaches itself to the bubble on that schematic. So you got to understand this product is actually, I think it's 10 years old, and it started back with Boeing, and it was originally called IntelliSchematic, but we have upgraded and changed the patent, improved beyond measure from what it was, and we continue to do so. We recognize that it has to be sustainable for you, meaning that in a day you need to be able to manage that, if you want to, very easily, all on your own, easier than you could do it with some of your own people there. And that's why, not to go on and on about this, but that's why schematics never get updated. They get hung on in a map room or a schematic room or in somebody's locker, and that's it. You know, that process has to change, and it's crazy not to change it in the technology age that we're in right now.
Yeah, and I'll say as a customer of yours, one of the things that I'm most impressed with, this goes right to the heart of Andy's question, is how quickly your team responds to questions and changes right there on the thing we're talking about here. You have the report changes down on every page. And literally, even when I'm messing around showing people, I've shown this across my company to many people. I'll hit that, type a quick little message to Wes, and he literally receives it within minutes, and lots of times answers it right away, even if it's just a test. You know, he doesn't know that I'm going to do it. He just does it. Or I do it and he instantly does it. Now, when we have given revisions, oftentimes those revisions are in place within hours, if not maximum 24 to 36 hours. Wes has everything updated, and that change is now live, and he holds on to what the previous information was. Brett?
And we have a reasonably large, across the country, network of SMEs that work for us, with us, that are assigned to do this. So we're very scalable in the process.
Yep. I am most impressed with how quickly they can do these changes. Now, and with that, Alloy TS, Wes, and all these SMEs, they can take care of those changes and they can manage them for you. Or at some point, we can manage them ourselves if we want. My company has chosen to continue to utilize Alloy TS to do these changes. It makes the most sense because I need my guys on the floor looking at the equipment, not in the background doing what these guys are the subject matter experts of. That's my blurb from my company. I can't pronounce this gentleman's name. Venkatish. Anyway, we'll get it. Retrofit for Industry 4.0 application for existing machines is possible without changing the components. Brad, I'll take this one. Yes, you can absolutely retrofit any age of equipment up to Industry 4.0, adding sensors, adding various technology, whether it's wired or wireless, pulling that into your PLC or adding something alongside. I've had the ability to travel around and look at a lot of our large OEM providers of a lot of our equipment, and I see gearboxes, power units, various components sitting on their shop floor that were created decades ago that are being updated with modern sensors so that we can understand what's going on with it. It's something that has to be done over time. It's scalable. You can do it at your pace. So it's absolutely possible.
Very good, gentlemen. I think we're approaching the 60-minute limit. I have a very quick slide to show Brad's email address. If I can take over the screen, Brad. So we want to thank you all, attendees and presenter Brad, moderator Steve, for an hour-long dive into the iMachine and the hydraulics controlling in the future. Brad, if you don't mind, people will mail you questions directly, and the link for this recorded session will be available on the AIST website. Give us a couple of days for moderating the software a little bit. But we also want to indicate that we have some upcoming things for this technical committee. This technical committee is the Lubrication and Hydraulics Technology Committee. We have a second seminar scheduled for Wednesday, the 22nd of July at this time frame again, actually 1 hour later. And we do hope to see you all plan in person at the AIST Tech meeting on the last day of August and the first 2 days of September in Cleveland, Ohio. There are additional webinars available through the website. Visit the AIST.org, the calendar feature for specific details. Again, we want to thank you all. Thank you, Brad, Steve, for your presentation, and we hope to see you again at the next webinar session. Have a good day.